Hey, so welcome back. We're continuing our rotational unit, and right now we're going to be talking about kinetic energy in a rotational sense and conservation of energy along with that. So to begin though, I want to ask you a question. Does that spinning hook kick right there that you see that guy doing, does it have the ability to do work on that object that it's colliding with? The answer is yes, of course. And if something has the ability to do work, to apply a force over a distance, or to cause change, then we say it has energy. It stands to reason that this guy has rotational energy with that kick. And so, of course, that's the case. And that's going to be our topic for this lesson. So let's get started with it. First of all, our equation for rotational kinetic energy is going to be here. So it's going to be 1/2 times the moment of inertia times the angular speed squared. And it has a very close resemblance to the translational version of kinetic energy, something that you're already familiar with over here. That's very important to remember. One thing I do want to mention before I forget is that I want you to remember that energy is scalar, measured in joules, so our direction doesn't matter so much with this. Let's continue and see how this modifies our mechanical energy equation. So you may remember that mechanical energy is going to be the sum total of our kinetic energy and our potential energy, and it's equal to zero. The change in mechanical energy is equal to zero when there are no non-conservative forces. Like when friction is not around, essentially, our energy, kinetic energy, and potential energy is going to be conserved, you could say. And we're just going to add one more aspect to this. In terms of, we're going to essentially break up kinetic energy into two parts here. So we're going to have a translational component and a rotational component. And as long as we can do that, we can set it up like this. And so you notice you have your initial variables over here, your final variables over here, and we can do interesting problems with that. So let's try a problem and see how it goes. Alright, and so our example problem here is going to be that a solid ball is at the top of a ramp. It rolls down the ramp. And this is modeling real life more closely because as it rolls down, it does have rotational kinetic energy and it does have translational kinetic energy as well. It has both. And so it's not fair to say that this is all going to be translational kinetic because it's rolling as it goes down. So notice we're more closely modeling the real world as we get farther into physics. The first thing I want to do is write down the concept that our mechanical energy initial is going to be equal to our mechanical energy final. And so that entails what we had talked about previously. So we've got 3 initial terms and we've got 3 final terms. And with this scenario right here, we can drop out the first 2 terms. Why is that? Well, this starts from rest. And if it starts from rest, it has no translational kinetic energy, no rotational kinetic energy initial for either one. And at the end, it has no gravitational potential energy compared to the 0 point on the axis. So what I'm doing is I'm assuming that this is going to be 0 height right here. We can set that as 0 height when we're dealing with the Earth, and that is recommended because that'll get rid of a term for us and make the problem much easier. And so what we're left with is this. I've just gone ahead and written in what the values are for these equations. So we have mgh, 1/2 mv squared, and 1/2 I omega squared. All right, so fair enough. Normally at this point, for a regular translational conservation of energy problem, oftentimes you can cross out masses. At this point in the problem, we cannot do that. We're actually going to change some of the rotational components over here into translational components, and then we'll later be able to cancel out our masses, but we cannot do that to start with. All right, so let's think about what we can do though. We can go ahead and substitute in what our I value is for a solid sphere. Our moment of inertia for a solid sphere is going to be right here. So that's as far as we've gotten at this point, and I'm going to label this as equation 1 as we change to the next slide. Okay, and so let's think about something we can do. I do notice right away that we have these fractions. We can simplify here, but more importantly, we want to start thinking about what we mean with this omega squared business. And this is the crucial step to the entire screencast. This entire lesson is coming up right here. This is the thing that I want you to remember for doing these types of problems, and that is this. We do have this equation on our equation sheet for AP Physics C, and if you take a look at this, we are saying our tangential speed over here is going to be equal to the radius times the angular speed. So this is a rotational component, this is a translational component. In one equation, we've got both a rotational component and a translational component. That's pretty rare. There is an analogy I can make with forces, where we oftentimes don't have forces in 2 dimensions, but in the case of friction, we do. We have friction, usually it's going to be in the x and the y. The x for a frictional force, the y for our normal force, and so that's a pretty special and useful equation. We have something similar here. We have this speed over here in a translational sense, this angular speed over here in a rotational sense, and so we're going to go ahead and isolate for our angular speed. And if we do that, we're going to end up with this. And this is the point at which I had mentioned earlier where mass is going to be in every term. Now we can go about canceling that out and thinking about how to simplify this with the end goal of getting our velocity. We want to get the velocity by itself. One of the things we can do is get rid of radius squared. We can get rid of the radius squared here as well as the radius squared here because of the power to the 2 over here. And all I've done is just gotten rid of the radius values and simplified slightly. But you can start to see where we're going with this because again we're looking for our speed that is in 2 terms on the right hand side. Okay, and so we continue with the problem. We will get rid of our masses formally and we're left with this. Now it just becomes easy algebra cleanup stuff. Notice that we're going to want to have common denominators and we're going to set that up and then combine like terms. And then based on that, we can isolate for our unknown and we can plug our numbers in and get a solution. So it's really not that tough. It just takes a little practice. I do want to review with you the key strategy that we're going to use for these types of problems. I'm assuming you already know how to do basic conservation of energy problems based on translational motion. The key difference here, though, the thing that we're building on, was this. The key thing that I want you to think about is, remember, we have this connection, this equation, this connection between the translational speed and the rotational speed. And so we're going to use that. We're going to isolate for our angular speed over here, and we're going to sub in what that is equal to over here to be able to continue and do the problem. That is the crucial new strategy. And as long as you can remember to do that, maybe you practice this a couple times, you're going to be totally fine. This is not that tough, but you have to remember to be able to do this. So I'm going to continue with more screencasts. Hopefully this has been helpful, and I hope you listen to the next in the series.